The results of our analysis now has another level tied to variation in the rate coefficient. So if we look at the results, I can click on results. That will call view with a capital V on results. And I see that the results is a list with 3 different elements, and these 3 elements correspond to different initial concentrations. And then for each initial concentration, we have 3 more elements underneath that element corresponding to 3 different levels of the rate coefficient. And then under each one of these, we have the results of a given model with, in this case, the rate coefficient is 0.05, the initial concentration is 25, and the results from that analysis. The second one here will be the same initial concentration, 25, but the next rate coefficient, which is 0.1, and the results of that. So with this structure, we've broken our graphing code again. Our graphing code is not expecting this structure, so we have to go to our graphing code, which is under this product.r script. And we have to think about how to change our graphing code to be able to deal with this data structure. So we're loading our results in just as before, but now our results have this extra layer in the hierarchy that we didn't have before. So then we have to think, well, how do we want to handle this in our graphs? Well, right now, the graph that we're creating is just a single graph with 3 different initial concentrations. We could make a single graph with every combination of the initial concentration and the rate coefficient, but that might get a little busy and might be hard to read. So instead, let's think about making several different graphs. And in this case, because of our hierarchy, let's think about for each graph, we'll make a graph that corresponds to a given initial concentration, and on that graph, we'll look at the effect of having 3 different rate coefficients. So we'll build a graph that has the same kind of structure of hierarchy that our data structure has. So let's think about how we do that. First of all, we have to look at the code that is doing something like what we want one time through, but we need it to do it several times through. Now we have code in terms of reading our results. Well, we only need to do that once. We are defining our PCHs. We're going to have to change how that's defined, but we'll come back to that later. We're opening up our graphics device. Well, we only need to do that once. We're going to create several graphic plots in this one file, so we don't need to be opening and closing our device because we don't want to make several different files. We're going to put several graphs in the same file. Also, we're going to keep the same graphics margins. We don't really need to change that from one graph to the next, so this doesn't need to be inside the loop. But here's our plot new, and if you remember what plot new does is it advances to a new graph and it gets ready to draw on that graph. And when you do that for a PDF device, that creates a new page in the PDF and starts a new graph on that new page. And that's exactly what we want to do each time through our loop. Each time for a separate initial concentration, we want to create a new graph. So this is probably where our loop is going to start, at this plot.new. So I'm going to leave the cursor here, and I've got all of my code for determining my xlim and my ylim. We're going to need to do that every time for each graph. We're going to need to create our coordinate system for the graph. We want to draw a box around each graph and add axes for each graph. We also need to create labels, and we need to do the plotting on each graph, the loop that does the plotting. We're going to have to change some of the details here, but we still generally need to do this for each graph. We need to label the axes of each graph. And finally, we need to put a legend on each graph. But here's our dev off. So we don't want to call dev off every time because we're only creating one file. So this is probably what we're going to do after the end of our loop. So if I hit shift here in space, I've selected everything. Oops, it looks like I moved the cursor earlier. I'm going to have to try that again. I want to go from plot new all the way down here to right before dev off. These are all the things that we need to repeat each time through our loop. I'm going to go ahead and tab, so these are indented over, which they should be if they're inside a loop. And then before all of this code, I need to start a new for loop. Now in this case, what we're going to do is create a new graph for each different initial concentration. So we need to think about our results as being what we need to pull from, the results list, there we go, as what we want to iterate through. So in this case, I'm not going to use the index strategy. I'm just going to use R's capability of saying I want to go through every element of this vector for this loop. So I need to go through all of the results for each concentration in this loop. So basically what I'm saying here is I want to iterate through each of these three elements that are corresponding, each one is corresponding to a different initial concentration. Now I need to specify all the code that needs to repeat for this loop with curly brackets. So I'll put 1 here with my for loop, and I'll go to where I'm no longer indenting and add my other curly bracket to tell R that all the code within this curly brackets is what we repeat, and it's indented so it's really easy to see where this loop starts and stops. So we have this loop all set up, and now we're iterating, and now we have to rethink what's going on in this loop, because previously the code inside the loop was based on this results, but now it needs to be based on this results.concentration. So let's look at where we have results. Well, first of all, we need to change this. We aren't going through the base results anymore. We're going through each results corresponding to a given concentration. Otherwise, all of this code is the same. Recall that what we're trying to do here is go through each one of the elements of this element and go through the contents of these to figure out what are the minimum and maximum values we're going to have on our X and Y axes. So this code is doing exactly what it's supposed to. It just needs to do it with our results_const each time through this loop, as opposed to the results in the base layer. So this should be all we need to change here for this particular code. The next thing we need to change is right here. So this is the loop we have set up. Previously we were going through results to think about how the model was changing with the different initial concentrations, but now we're looking at results_const because we are looking within each concentration. We need to know something about how the different rate coefficients are affecting the curve. So again, instead of results, we're diving in one layer and we're looking at the results for each initial concentration. So I need to change this to results concentration and this to results concentration. Also, it's a little confusing to call this const index because this index is not changing with concentration anymore. It's changing with the reaction coefficient. So I'm going to show you real quick a way to refactor code. We want this block of code everywhere in this for loop. What we're currently calling a const index. Instead of const index, we want to call it an RC index or a rate coefficient index. So I'm going to highlight const index. I'm going to hit a Control F on a PC, and that brings up the search bar. And in RStudio, the search bar is also how you search and replace text. So automatically const index is what I'm searching for, and I can go to the next or the previous, but I can also use this tool to replace the text. And I want to replace it with RC_index because now the variation in the index is corresponding with variation in the reaction coefficient, not the concentration. Now, if I have this filled in this way, then the const index that I'm currently on that I found with my first Control F, I'm going to replace by hitting this replace button. When you replace it, notice it took the const index out and put RC index in, and it automatically found the next const index. So here's the next one. I need to replace that one as well. There's the next one, replace that. There's the next one, replace that. And it asks you for each one just to make sure you're double checking that you really want to replace it, which I do. And now it can't find any more occurrences of that particular variable, so it tells me so. So that's just one way to help you quickly find and replace things when you know you need to refactor a particular variable name. So I do want to go through results consts here. I've already changed this, so I'm cycling through all of the elements or the indices of the elements of the results consts for a given concentration. And then for each results concentration, here's another thing I need to change. I'm not using just results. I'm using results_concentration. Same thing here. because I need to go to the individual results concentration, and then I need to go to the particular index corresponding to each rate coefficient and get the times. Do the same thing for the concentrations. And finally, get the right PCH for that particular rate coefficient. Now here's an issue, because our PCH before was defined by however many initial concentrations there are. Now we need them to be defined by however many rate coefficients there are. So we can go back up and let's move this code. Originally, we established PCHs early in the code, but now we're not basing it on the base results anymore. We're basing it on the numbers of a number of results for a given initial concentration. So let's copy or cut this code and paste it back in. And this is something that we can do within this loop. So let's do it at the very top. We've got our PCHs, and this is no longer tied to the results, but it's tied to the given results concentration we're working with. So each time through our loop, we're going to define what the PCHs are based on however many results there are under a given results corresponding to a given initial concentration. So now we're back here. That's going to make sure we have the right PCHs to put in corresponding to each rate coefficient. And finally, our labels here is going to be the labels for each RC index, and it's going to be as character. And again, here we need our results underscore concentration, not results, at a given RC index. And instead of the initial concentration, remember what we're varying here is the rate coefficient, not the initial concentration. So remember, this is for building the labels for our legend such that we have the actual value of the rate coefficient corresponding to each PCH or each symbol. Okay, I think that takes care of everything inside this loop. Everything should be fine here for our title. That's not changing. We're still plotting concentration versus time. But what we do need to change is our legend, because previously our legend was talking about how each PCH was associated with a different initial concentration. Now we're talking about it being associated with a different rate coefficient. We've already updated our labels. That's right here. We made sure that we're getting the value of the rate coefficient for each model result to include in our legend. But this is incorrect. The title, this is no longer variation in the initial concentration. It's now the variation in the rate coefficient, which we specified in our mathematical notation as a K sub R. So this is our rate coefficient. And these units are not correct. Instead of it being milligrams per liter, it just needs to be per minute. So we can use all of the notation we had before for the per liter, but change the capital L to a minute to specify a per minute for our rate coefficient. So we have added a loop around everything in order to make a new graph for each initial concentration. And then inside that loop, we've altered our code to cycle through each rate coefficient and make sure we have the right notation. So let's see if we've done this without any bugs and we can run the code. Well, it ran clean. Let's go ahead and look at our graph. I'm going to go back out to our product folder and bring up the visualization. So here's our first graph. We have concentration versus time, and we have three symbols again, but it looks different than before, because now we have one set initial concentration. In this case, we're starting at 25 as our initial concentration. But we have three different rate coefficients. We have 0.05, that's this more gradual change in reactant. We have 0.1, that's a steeper change in reactant. And we have the 0.2, and that's the steepest yet. So this should make sense. If we're changing by 5% per minute versus 10% per minute versus 20% per minute, we should see a steeper and steeper decline in our exponential decay. And if we scroll down, we should have more than one graph. We can see how the PDF, by putting several different plot new functions, is creating several new graphs. So we have another graph where now we're starting at 50, but we have three different decay rates, 0.05, 0.1, and 0.2. And we can see again the 0.05 is the less steep, and the pluses for 0.2 is the most steep. And finally, the last graph, we're starting at 100, and again, three different decay rates. Now you might note that there's really no difference between these graphs other than the scaling on the axis. They look exactly the same. It's just that the scaling on the y-axis. Well, that tells us something about how exponential first-order decay works. We're dictating how these change by a relative amount. We're saying they're changing by 5%, by 10%, or by 20%. That means you are going to get to the same percentage remaining at the same time, no matter what value you started at, because you're changing by a percent. So we're getting to half of 25, which is 12.5 at about, let's say that's about maybe 13 minutes. We're getting half to 50 at 25, again at about 13 minutes. So these graphs look exactly the same other than the fact that we're rescaling the y-axis, and that's exactly what you would expect for a first-order exponential decay. We might want to do one more thing to make it easier to read the graphs, because we've changed our legends to tell us how the rate coefficient is changing, but now we've lost any labeling that tells us anything about how the initial concentration is set. We can infer how it was set based on just looking at the graph and the axes, but perhaps we want to make that crystal clear, like if we were putting this into a manuscript for a journal or something. We want to make sure it was really clear how these represented our different treatments of our different experimental units. So let's look at how we might add a label to each one of these graphs based on which initial concentration we are using. So we're going to be in the same loop. Remember, we're executing a loop that we're going through once for each initial concentration. So at the very end, it probably makes sense to put our code for putting some sort of label on the graph. And remember, we've reset our coordinate system, so it's really think about where this label is going to go based on the x-axis being bound by 0 and 1, and the y-axis being bound also by 0 and 1. So a function that we can use to add text to a graph is simply called text. And text is for adding to a graph somewhere within the graphing area. So within this box, text is the easiest tool to use for adding text somewhere within this box. And we know for these graphs that we're going to have some room up in this upper left-hand corner. So let's go ahead and stick a label in this upper left-hand corner that tells us what the initial concentration is. So if we do a help on the text function, you'll see that you have an x and a y value just like you do for legend. And again, that's going to be telling R where you want to put this particular text. And in this case, we want to put it at 1, x equals 1, y equals 1. That's going to correspond to this upper right-hand corner because we've rescaled such that we're going from 0 to 1 on our x-axis and 0 to 1 on our y-axis, which would put 1, 1 in this upper right-hand corner. Similar to legend, there's a way to tell it where to put the text relative to that coordinate. Unfortunately, it's not called the same thing as legend. It's not x just and y just. You need to use the ADJ argument. And the ADJ argument can take a vector of two values. And here's where it works similar to the x just and the y just. Again, you're telling it where to orient the text that you're putting relative to the coordinates that you're giving it here. And we want it to be right justified according to the x-axis. That means for the x, we need to put a value of 1, and we want it to be top justified for the y. So we want the top right corner of our text to be right on top of this 1, 1 coordinate. So that means we need to adjust relative to 1 for the x-axis and 1 for the y-axis. That means we're right justifying for x and top justifying for y. Now we need to figure out the actual label that we're going to apply with this text function. So I'm going to need some more room here. I'm going to go ahead and put each argument on its own line. And keep a narrow code style. I'm going to have my closed parentheses at the same level of text and indent my arguments so it's really clear where I'm stopping and starting this call to the function text. And I need to add the argument labels. And this needs to be a character string that's telling it what text to put at this location. Or in this case, I want to put in an expression because I want this to map to a given initial concentration. Now, in order to show that, in terms of the value of the initial concentration, I'm going to need to take a value out of my results data structure and put it into the label so that this text reflects the concentration that I'm talking about. And in order to do that, I want to use a different function for building the expression because there's another function that makes it easier to include our code in your expression that will specify some particular text that you want to show in the label. So in this case, I'm going to use the bquote function. And a bquote function will create an expression as well. And how I need to create that expression is similar to what I'm doing here. First of all, I need this italic. I'm just going to copy and paste this because I want to do something very similar to showing the variable name like I did for the rate coefficient. But in this case, it's going to be an initial concentration. I want to say that's equal to something. In plot math, you need two equal signs to specify a single equal signs in the mathematical notation in the rendering. And then here is where I want to put in a value for this C0. And with bquote, the way that you put in a particular value from our code is with a period and an open and closed parentheses. So anything inside these parentheses, it's going to interpret as our code and substitute that value into the expression such that when it builds this label and puts it on my graph, it will have the value that was in the R code. So in this case, what I need to do is go to my results underscore const, and I need to go to a particular element. If you recall, each one of these results underscore const is one of these elements here. And I need to go into one of the three elements of this list element because I ultimately want to get at this initial concentration value. So it doesn't matter which one I go to. I know it's going to be the same for all three of these. So I'll just go to the first one. And then I can put in the $sign to specify a particular element of this list, which is going to be this const init value. And that const init value I know is going to correspond to the number that I want to put into this expression such that my label will have the value of the initial concentration for this particular graph. So let's take a look at how this works. If I save it and run it, I can go back to my graph and it's refreshed. I have a C0 equals 25 on my first graph, which indeed, this is the initial concentration 25. On my second graph, I have a C0 equals 50, which is indeed the right initial concentration for this graph. And finally, a C0 of 100, which is indeed the correct initial concentration for this graph. Now, the last thing I might want to put on here is some units. So let me go back to my code. And after the number that I have for the initial concentration, I might want a little bit of space between the number and the units. Remember, we're writing an expression here. So in between elements of mathematical elements, I need to put either an asterisk or a tilde in order to tell it there's another element coming, and the tilde means there's space, an asterisk means there's no space. And the units here are going to be milligrams. We need a little space between milligrams and our per liter, and then an L and an exponent with a milligram per liter. So again, this is telling in our expression, this is telling plot math, I need some space before you put an mg, some more space before you put a capital L with the exponent -1. So if I run this one more time, go back to my graph, now I have units on this label that I've put in my graph, 100, 50, and 25. If you want to challenge yourself, you can put this text outside of the graph. There's a couple different ways to do this, but if you use the XBD, you can use text to do it. If you want to challenge yourself to figure out, if you can figure out how to put this here in this margin, increase the margin and put the label outside the graphing area, that might be something that would be fun to try.